Hi guys, and welcome to Codeforces Div 2 round number 791. So I'm recording it the next day because, as you can see in contest, I solved first 5 problems, which was actually reasonably good for me, at least. And then for last problem, I got some correct ideas but couldn't implement it on time, so I had to upsolve it later. And I couldn't upsolve it yesterday because I had other contests to attend. So before we jump into this editorial, I wanted to ask you, which topic do you like more, dynamic programming or graphs? So it can be any dynamic programming problem or any graph problem, because majority of contests have both. So yeah, I would like to know which one you like more. Comment down below. So let's take a look at the problem A. In problem A, we had some buses. Some of them had 4 wheels, some of them had 6 wheels, and we know that overall there are n tires. So like 1 tire per 1 wheel, usually. This is how it goes. So we needed to find the minimum and maximum number of buses that could have been, like if we only know the total. For example, 24 you can represent as 4 times 6 or 6 times 4. So 4 6-wheeled buses or 6 4-wheeled buses for minimum and maximum number of buses respectively. So in this problem what I did is, you know that if you take all buses to have 6 wheels, then you will get approximately n over 6 buses, right? It's clearly optimal. If you want to minimize the number of buses, then you want your buses on average to have as many wheels as possible. So you try to take all of them to have 6 wheels. So from that you get some approximation. However, your original approximation may not be divisible by 4. So like if your number n is, for example, 8, right? You can take one 6-wheeled bus, but then you'll end with 2 tires, which you cannot distribute into 4-wheeled buses. So you need to actually ensure that your approximation, well, is, first of all, it's good, and then like remaining tires can also be distributed among the other type of buses. So from that you get one approximation for like minimum number of buses, from starting with as many 4-wheeled buses as possible and going until you get a remainder to be divisible by 6-wheeled buses. You get approximation for maximum number of buses. So yeah, once you're done, this is just computing based on our approximation. What is the number of buses? So that's like 4 wheels, and that's remaining 6 wheels. The only tricky case in this problem was like sometimes it's not possible. So in this case, it was not possible, obviously, if the total number of tires was odd, and the only other case is n equal 2. So actually all even numbers starting from 4 you can represent as sum of some number of 4s and some number of 6s. This is not hard to prove by induction. A bit of a long editorial because I wanted to show this technique of like taking approximation and then adjusting it. Let's look at problem B, if it can load. So in this problem we had array, and we needed to support 2 types of operations. One was replace some given element, and second was replace entire array, so like all elements. And after each query we needed to print the sum. So there are multiple ways to do this problem. The way I did it, I start like for each array we can look at it as follows. It originally consisted of 1 value, and then we made some number of updates. So let me store this value and let me store updates, which say like, oh, at this position, actual value is new value. And I also keep track of this sum. So originally, we can look at the original array as like, we had value 0 and then updated all entries accordingly. And we process queries. If we update elements, right, that was not previously updated, so like then its value is equal to common value for the entire array. And then update is as follows. First, we need to remove old element, then we need to update it, and then we need to add new element. And whenever we assign one value to entire array, we obviously get our sum equal to this new value times number of elements. And we also forget about all positional updates. So yeah, that's the way to do it. And this is also a common idea to store small changes between different states in time of your structure. Like, if you cannot update explicitly, like assign loop over each value in the array and assign something to it, then you need to somehow work with a compact representation. And in this case, compact representation is like, well, entire array is equal to value except for some positions. And this is the general principle, that you want to store some small differences. It is generally helpful in square root techniques, but that's a bit advanced. For this problem, all you needed was map. Let's take a look at problem C now. Problem C actually appeared before, and I've seen it before in some very old contest, and it is just a standard problem. In this problem, you have a checkerboard, and you place some rooks on it, and you get queries of the form, hey, is every cell in this rectangle covered by one of the rooks? Is it attacked by one of the rooks? So of course, to solve this problem, you first need to realize that the entire rectangle is attacked by rooks if either every row or every column of this rectangle is attacked. Why this is so? Well, assume that there is one row and one column that are not attacked, then obviously their intersection is not attacked. So this way we decomposed problem into rows and columns. And now we can actually start doing something. So this is just template code, library code for find victory, which we'll need later, because you can think of what does it mean for every row or every column to be attacked by a rook in a range? Well, it's obviously range queries. But if you just try something like range sum queries, then it will not be correct because one of the columns or rows may contain multiple rooks, and you don't want to count them twice. So what I did for this, I just store the number of rooks in every row and every column. And then for fenwick trees, I only process update when it changes significantly from 0 to 1 or from 1 to 0. So you can see this is adding a rook. So first I check if there hasn't been a rook previously in this row, then I need to process fenwick tree update. Same with column. And then I can update frequencies. When removing, I first decrease frequencies, and then I see okay, if there is no longer a rook in this row, but obviously there was a rook before, then I need to subtract 1 in fenwick tree. And then I just check whether it's true that all rows or all columns are attacked. So in many grid problems, it is important technique to decompose whatever you have into rows and columns separately. I hope you remember this technique. In problem D, we had, I believe, a graph. Each vertex of this graph had a label. The graph was directed. And we wanted to find a path of length k in this graph such that maximum number along the path was as small as possible. So the way to do it is binary search, and specifically I implemented the version of binary search where you can search over all possible values, right? From 0 to 10 to the 9th. But it may be sometimes slow, and I have a habit of writing a code with bad constant. So I thought in this case, let's do binary search over all labels. So clearly the maximum number along the path will be one of the numbers written in vertices, so you can actually do binary search over n numbers instead of 10 to the 9th, which is just a little bit faster. Maybe I don't know, 30–40% faster. Not significant, but as you can see, I just had the feeling that in this problem runtime will be kind of high. So I decided better to be safe than sorry. Then we do binary search. What will be our binary search? Well, we kind of had graph that is reduced, that contains only vertices that have small labels. And then for this graph, we will need to do some dynamic programming to find the length of the longest path. Because clearly a path of length k exists if and only if the length of the longest path is at least k. So how to find length of the longest path? Well, it's obviously dynamic programming in topological order. So here goes my standard topological sorting algorithm, compute in degrees, get yourself a queue of vertices, update in degrees. When degree reaches 0, vertex can be put in order. There is only one tricky case, top order basic obviously doesn't always exist. But if it does not exist, then it means that our graph contains a cycle, so longest path is infinite. So obviously there is as well a path of length k, so we can immediately return true without doing any dynamic programming. Otherwise, you do your dynamic programming, very common to compute length of the longest path. You can define it, dynamic programming, as length of the longest path ending at given vertex. Then you have obvious push updates. And whatever is the maximum, if it's at least k, then good, we found such an edge. Another tricky case in this problem was if you do not have, even considering all vertices, you do not have a path of length k, k is too big. Then the answer was -1. But it also can be checked with the same function. You can see, by the way, it is another important trick. I could have created graph explicitly here for each value of middle that I check, but it may be a bit slow. So instead, because it will use a lot of memory, this graph uses of m memory times log. It should not be a problem, but again, I had the feeling that I may run into issues, so I decided to be safer. So I don't construct graph explicitly. I iterate over original graph and then check if vertex is good or not. If our destination actually belongs to our subgraph or not. This could have been optimized by sorting. So when you encounter your first label that is too big, you can break, but whatever. This is kind of a heuristic already. Whereas not constructing graph explicitly generally helps, provably, because you don't need that many memory allocations. So yeah, that was problem D. Then problem E was another interesting problem. Here we had some string with question marks, and then we had multiple queries. In a given query, we were given a string, and we were allowed to replace every question mark with one of the characters in the string, and for each such replacement, we counted number of palindromic substring of the result, and then we needed to add all of this together. So I noticed that we only have 17 characters of the Latin alphabet, which obviously hints towards using something with 2 to the power 17, because otherwise there is no need to restrict your alphabet like so. So by now we already know that it is some bitmask dp modulo, so I copy pasted at coder library mod int for that. And then we can think, like, how do I know for each basically mask of characters, right? For each mask of characters, I needed to count all palindromic substrings that can be obtained. So I thought, like, counting for masks is kind of hard. Let's count from substrings. So let's consider every substring that can potentially be a palindrome. And for each such substring, let's find minimal mask by inclusion. Such mask obviously exists, such that if, like, we need these characters, absolutely we need these characters if we want our substring to become a palindrome. So for this, what we do, we consider all substrings and just like optimization sync, we expand them from middle. This is common approach. So we take middle and we expand. This needs to be done separately for odd and even values, of course. Oh, yeah, I'm pretty sure that you can like reduce code duplication here, but I was not thinking about this in context. So I keep track of minimum mask, and I also keep track of how many replacements we'll need to make, because this will come in handy later. So what I do is I check, like, for each pair of new characters, if they are different and one of them is replaceable, then it must be replaced with the other. If none of them is replaceable, then it's not possible to make this substring palindromic, no matter what mask of characters we are given. And also, if both of them are replaceable, then we kind of have a limited choice, in a sense that once we fix one of the question marks, the other gets fixed as well, so one more replacement is kind of forced. So by now we know for each substring what is the minimum mask that needs to be present in order for this mask, for this substring for it to be possible to become a palindrome after replacements. However, like, this obviously hints towards subset sum dynamic programming, or SOS as some people call it. So subset sum DP is like this. For each mask, it counts sum over all submasks. This is a very common technique that you absolutely need to know. So then we'll be able to, like, just look up the value at the given mask. However, I needed to count not how many distinct substrings can become palindromic in terms of left and right position, but also, like, let's say substring does not contain any question marks and is already palindromic. Then it must be counted multiple times with the frequency equal to the number of replacements that yield a palindromic substring afterwards. So, like, each substring is counted with some frequency. And to count this frequency, we need to keep track of how many replacements we made. So there will, like, those replacements are forced. Or there are total number of question marks minus forced replacements that we have a freedom of choosing. And if our like mask that we are allowed to replace in the queries, if it has some lengths, then each of those question marks that remain, that are like not forced, it has the corresponding lengths ways to be replaced. So basically, I do this same dynamic programming for every length, from 0 to length of the alphabet. And it works in of n squared times 2 to the n time, where n is, it works in O of n squared, where n is the length of the string, plus alphabet squared times 2 to the power of alphabet. It's just like 17 squared times 2 to the 17th, fast enough. So, and this was important to realize that for each length you need to count separately, because if you don't keep track of how many different replacements for each character you have, then it's not possible, I believe, to restore like from pure masks without having lengths. But it was just a very natural parameter to introduce into your dynamic programming, so that's why I did it. I know it may be a bit confusing, and also the editorial for this problem is quite long, as well as the code, because it contains multiple ideas. Try to go over them in order. For count over substrings. For each substring, minimum mask. Then count number of replacements, then subset sum dp. Substrings you can process efficiently expanded from middle. A lot of ideas, but well, that's div 2 problem E, which is kind of like div 1C, so it is expected it is quite hard. As you can see, a lot of people either couldn't solve it or ran out of time. Now, problem F was quite hard, not gonna lie. In problem F, if it can load. So once again, there was some modular stuff. So in problem F, we wanted to count, oh my. What's happening? Okay, so in problem F, we were considering integers of, or better say strings, of length n that consisted of digits, including leading zeros. Besides that, if we were allowed to swap consecutive digits in these integers as follows. If we were given a certain number of pairs such that we can swap adjacent characters if they form these pairs. For example, if we're given 1, 3, then we can swap 31 into 13. If we were given 0, 2, then we can swap 20 into 0, 2, right? But only consecutive pairs of characters were allowed to be swapped. So you can see here, only consecutive characters you can swap. So we needed to find number of equivalence classes. Obviously, these kinds of swaps are always reversible, so they form an equivalence relation. And we wanted to count the number of equivalence classes. So basically, how many different numbers you can come up with such that none of them is transformable into other via the operations. So I actually got some important ideas for this problem in contest, but couldn't finish it on time. So constraints clearly hint toward complexity of n times 10, because there are 10 digits, times 2 to the 10s, because we will need some masks of digits. So in contest, I wrote some DP like this, And then I was not sure like how to process updates. So that means that we have like we build in a prefix or a suffix better said of given lengths. We have some mask that describes our suffix, and we are trying to add one more digit to it, prepend. So this was obviously not always possible, but if it was possible, then such an appendment always yields some given new mask. So you can understand that something like this is going to work, right? Because if it is possible to describe a suffix with one bit mask, and based on the constraints of the problems, it was kind of like, it must be possible. So now we just need to figure out what does it mean that it is possible to prepend last to mask. What will be the new mask once we prepend last to mask, and also what is the meaning of mask. So in my solution, the meaning of mask is like, once we get, I want have to count the number of equivalence classes. I want to count the number of representatives. So like for each equivalence class, I want to select one string of digits of length n that will be a representative of this class. And for the sake of like easily constructing a representative, let's say that we want each equivalence class to have its lexicographically minimal string as a representative. So we are concerned with like what is the lexicographical minimal string that we can obtain. So now let's think how we can construct a representative in such a way that it will be lexicographically minimal. It means that every time when we prepend last to mask, it must not be possible to swap last with like next element if last is less than next element. So first is like first element of the suffix, and last is the last element of the prefix. We are trying to prepend last to mask. So there must not exist a smaller element in mask such that it's possible to swap first and last, because then our current number is clearly not lexicographically minimal, so it's not a representative. So yeah, this was conditioned for like when it is possible. But you can say like, actually, if you only check first element of the mask, then why do you need entire mask, right? Then just store first element of your suffix. But you can, by considering examples, we can understand that sometimes you may need to shuffle suffix in some way, shuffle mask, and then some small element will become swappable with last, because these edges, they do not form cliques necessarily, there may be some more complicated structure, so you need to be a bit more careful. So mask is actually a mask of all digits that can become first in our suffix. Once we figure this, it's not easy to pre-compute new mask for each pair of prepended character and old mask. We are concerned like what can be the first digit of a suffix now. Well, obviously last can be, so we add this to mask, to new mask, but also all elements that are greater than last, if they were possible to place in mask, and if it's possible to swap them with prependable character, then we also need to allow this new character in mask. So that was it. And the reason why we need to pre-compute this is because here I need of-1 lookups. I cannot afford of digits, because then complexity will become like too big. But in this case it works. So yeah. Thanks everyone for watching, and let me know what you like more. DP problems like E and F or graph problems like D. Bye bye guys, and I'll see you soon with at Coder Beginner Contest number 251.